In this problem, we have a 1.7 kilogram block, that's the mass, because it's in kilograms. It's being pushed up a 25-degree ramp. Here is that incline, 25 degrees, at constant velocity. That's really important. That means the forces all balance, not just on the tilted y-axis, but also on the tilted x-axis. A person is pushing with a force directed up the ramp, as the diagram shows us. This diagram would be provided. The coefficient of kinetic friction is 0.380. Careful now, that's not the value of kinetic friction force. That's not Fk. It's the coefficient, which is mu k. Find the person's applied force, and here's the answer we should get. Okay, first thing we have to do is draw the other forces that are acting on the object. There's always the normal force pointing perpendicular to the ramp, and there's always mg pointing straight down. Next, we have to draw the components of mg, because mg is on a tilt, it's on an angle. It's at an angle to our tilted axes. And whenever we have forces directed at an angle, we break them up into components. All right then, one of the components of mg must be perpendicular to the ramp, and the other must be parallel to the ramp. The 25 degrees that we marked earlier shows up right here inside of the triangle. So that's 25, and that means that this tilted y component is mg cosine 25, and this tilted x component is opposite the angle, so it's mg sine. We took care of this angled mg force, so I can kind of squiggle it out because I'm showing it now instead with its components. Now the block is going up the ramp. There is kinetic friction, so I have to draw that final force. Kinetic friction opposes the motion. And it would be something like maybe this long, given the other forces I've drawn. All right, we know that the forces balance. So how will we find Fa? Well, let me see what equation I could write that contains Fa. If the forces balance, then the sum of the right pointing forces has to equal the sum of the leftward pointing forces. Which forces point right in my picture? Just Fa. Which forces point left in the picture? Well, there's Fk, and then there's also mg sine theta. So let me add those up on the other side. We've got Fk plus mg sine theta. I know mass, I know g, I know theta, so now all I have to find, is Fk, and I'll be able to calculate my applied force. All right, let's take that on. How do we find Fk? Well, we know kinetic friction is equal, the force is equal to mu times the normal force. But the normal force balances something. Look back to our picture. This tilted down force must balance the tilted up force because the block does not accelerate off the ramp or down into the ramp. It's not accelerating like levitating like this. And it's also not going this way, accelerating this way. It's not crushing the ramp. All right, so Fn balances mg cos theta. That right there in parentheses is the normal force. So now we could go calculate, well, you know what? If you want to be really fancy, you could just go ahead and plug in the value of mu, that's 0.38. Plug in the mass of 1.7, g is 9.81, plug in theta, and then get your answer, stick it right here, plug it in, calculate. Or if you really want to be fancy, here's what you might try. I'm going to write this equation again, and in place of Fk, now I put mu mg cos theta and mg sine theta on as the other term. If you take this route, if you combine everything into one equation, it is crucial that you show your work. Show this step, show these two steps and then finally you put it all together. You can't jump straight down to this or you'll lose points for not showing all of your work. Okay. All right. From here, we just plug in values. Mu is 0.3, what was it, 0.38? The mass was 1.7, right? G we know is 9.81. The angle is 25. Plus another mg sine theta. 25. And when we calculate that, hopefully it rounds up to 13. Or rounds down, it just rounds to 13. Okay, let's turn finally to number 8. These are wrong values, let's fix that. The picture would be provided, this would be given in the picture as 22, and you would have an applied force of 87 drawn into the picture. As always, we start by drawing the forces. We've got, I'm not going to read the problem, but they do give us mass, they give us the angle, they say constant velocity, so again, forces balance. They give us the applied force, and they ask for the coefficient of kinetic friction. Mu k equals question mark. First, we draw the forces acting on the block. Normal force is off the ramp like this, always perpendicular. Let me put my angle over to the side. Gravity is always straight down. And then we draw the components of gravity. So there's the tilted y component and the tilted x component. We know that the tilted y component is adjacent the angle. That angle that we wrote earlier, 22 degrees, the one that was provided in the problem, that shows up inside the triangle right here. So this tilted y component is adjacent. The tilted x component is opposite. We've taken care of mg, we broke it into its components, so effectively it's no longer there. Instead of putting it or representing it as an angled force, of course it's angled compared to our tilted axes. Instead of representing it as a hypotenuse or as an angled force, we break it into its components, or resolve it into the components. Okay, we're looking for mu, and mu shows up in this equation. But we know what Fn is. The upward pointing force must balance the down. So in place of Fn, we know it must be balancing or equal to mg cos theta. We know also, all right, so now look at where we are. To find mu, do we know mass? Yes, we do. Do we know g? Yep, 9.81. Theta we know. So before we can find mu, we'll just have to find Fk. How do we find Fk? We remember the fact that left-pointing forces balance rightward pointing forces. So in my picture here, oh, I forgot to draw friction. Oh, tragic. How does that happen? Ugh, because it's kind of late. That's probably why. And I should draw my friction arrow longer so that these two forces together, they should add to be balancing out the 87. Right now, 87 appears longer. So my picture is not great, but that's okay for now. Is it okay? No, it's going to bother me. Hang on. Something like this, I think. Right? Because now, if we take this force, and then we add this, do they add up to the same as the 87? Yeah, it's pretty close. Okay. So how do we find Fk? We balance the leftward pointing forces. There's Fk pointing to the left. Mg sine theta points to the left. We balance those against the rightward pointing force, which is just the 87 newtons. So we're using sum of the left pointing forces is equal to the sum of the rightward pointing forces. Pointing left is Fk we add with it, we add them up, sum any other leftward pointing, like mg sine theta. Pointing to the right, we have the 87. And we solve for fk, because we know mg, we know theta. M and G, we know. Okay, so should we do this? I'm just going to cheat here. I'll say fk is 87 minus, what's the mass? 14 times 9.81 times sine 22. And then I'm going to take that value, this expression, this expression here for fk, and I'm going to set it equal to mu times the normal force, which again we said above was m, 14, g cos theta. And again, theta is 22. We isolate mu by dividing both sides by the 14, the 9.81, and the cos theta. We divide the entire left side by all of that. And when we get our value of mu, hopefully it rounds to 0.28. Thanks for watching.